Hello, everyone, and welcome to the GeekNarrator podcast. I'm your host, Kaivalya Apte, and I'm back with another very interesting topic. Today, we have Jack with us, who works at Confluent and has many years of experience working on distributed systems, and more importantly, the topic for today, which is formal methods. So, Jack has been using formal methods for verifying system design and finding bugs in existing systems and new systems. And we are going to learn from him how it has helped in his journey. So, welcome, Jack. I'm really excited to have you today and
Yep,
excited
thanks.
to learn from you about your experience. So, let's start with a little bit of introduction and about your background and a little bit about what you do. And yeah,
Okay, yeah, I'm Jack Vanlightly. I am a principal technologist at Confluent, which is it's not a very clearly defined role, but basically I'm like a researcher, which could be anything from distributed systems research, replication protocols, or it could be things like market direction, where Confluent is headed, where the market is headed, what are competitors doing, what are they doing, trying to understand their technology, what are opportunities and threats, as well as longer term thinking. So I spend a lot of time trying to think what things will be like in 2 to 5 years, and then use that to influence direction in Confluent. It's a pretty functional role, anything from working with product engineering, the field, marketing, customer calls, and I do a lot of writing. So writing kind of underpins everything I do, and it's like my superpower. So I'm been a writer all my life since I was a teenager, writing short stories, science fiction stuff. I used to write poetry, songs, all kinds. I've just been a writer all my life. It's like a compulsion. I have to write. And so
yeah,
it comes all these years now of being a writer, it's definitely helped me express, explain things, but also think more deeply because, as they say, writing is thinking. And it's through
absolutely.
writing that I really, truly understand things better. So that's what I do at Confluent right now. It's not so much directly in engineering, but it's more of a research and influence within the company and writing. So
Yeah,
how I got onto distributed systems is, I guess, interesting because that's what I'm probably more known for. Especially, I tweet a lot about formal verification. But in terms of like how I got here, I've been an engineer for 20 years. It's really only the last 2 years I've moved a step sort of above that. But I started out in C++ and trading systems. I learned a lot about concurrency, performance, reliability. When things would go wrong, angry traders would literally come down to our floor to shout at us. So, as a junior, like that was a baptism of fire, but very influential on the rest of my career. But I then got into like data, and I stayed with data ever since. So my first kind of, I guess, my career changed after reading a book on SQL Server. I was a kind of application developer, and we were always having some problem with SQL Server, like deadlocks and stuff. And then I read a book on SQL Server locking fundamentals, which explained how B trees work, how indexes work, all the internals of SQL Server, query optimization. And after that, people were like, "Oh, we're having a deadlock," and I'd be like, "Oh, you just need to add an index. This is the index," and then boom! Oh my god, Jack, you're amazing! And oh no, you need to rewrite this query because it's not efficient the way it is. And learning the internals of how it worked made me like this. I was the guy. Right? I was the SQL Server guy. People would just come to me asking for help, and that felt pretty good. And so I just carried on learning about internals of Cassandra. I wasn't even using Cassandra, but I knew all of its internals, and it was really amazing to learn how it did replication and LSM trees. I learned about Neo4j. I started using Neo4j. Then I got into Kafka and RabbitMQ. And so all this was in the field, but at the same time, I was always learning, like, how did it work inside? And then using those internal knowledge, I could use it better. That then, I think it was in 2013 was the next big milestone for me, which was Jepsen tests. So the Jepsen tests, for those who don't know, basically Carl Kingsbury would use kind of his kind of tooling that would kind of mess with the distributed data systems like networks and kill nodes to bring them up and then analyze the results in a kind of formal analyzer. And he was able to basically demonstrate like, oh, this thing claims linearizability, but it doesn't, and here are the steps. And it was just amazing. It was just like, oh my God, I need to do distributed systems. It was the coolest thing. And then I was just a practitioner in the field. I didn't, so I just carried on learning and learning, reading papers, and then I got into actually distributed system testing of RabbitMQ using the techniques I'd learned from the Jepsen tests. So I took 2 weeks of holiday from my kind of day job to just work on RabbitMQ testing, and after that they just hired me. So I joined the RabbitMQ core team. And after that, I've not looked back. I've just been a distributed systems engineer since. I've been paid to work on distributed systems, break them in various ways using Jepsen style tooling or performance benchmarking to analyze how do they fall over under stress, to actually working on, I didn't really write code for RabbitMQ. I was a bit slow to learn Erlang. But when I joined as a bookkeeper and Pulsar contributor at Splunk, like full time, it was Java, so then I was contributing code all through this at RabbitMQ and Bookkeeper, like Splunk. I was using formal verification. I'll get onto the specifics of that. And now I'm where I am now. So that's a long introduction of how I got here. But I think it's actually quite interesting to see how people get into distributed systems, because I think there's many different avenues to get here. Some people can be lucky and they can land a job that happens to be on it, whereas other people just decide they want to do it and then they've got to kind of fight tooth and nail to get in to a team. But I think it's an interesting topic of how you get in, because it's not, I think it's got a lot better in recent years. There's a lot more blogs, there's a lot more writing about it, so there's easier to learn the necessary skills to get into it. But historically that hasn't always been the case.
Absolutely. Very interesting. And that's true. There are so many resources, but sometimes it gets overwhelming that there are so many resources where to start. But yeah, it's great to see that how your experience has been into these systems, and more like you're like a distributed systems hacker, understanding them internally and then trying to break them and finding bugs and then fixing them. It's very interesting. And so in this episode, we are going to learn from your experience, like how specifically formal methods have helped you and shaped your approach into distributed systems. A couple of episodes ago, we talked about FISB and how that tool can help improve or reduce the friction of someone who is new to formal methods, to give them an ability to write like Python like code and write formal verification and so on. So we'll also ask you about that. Before we do that, I want to understand from your perspective, how do you look at formal methods? Like when you talk about formal verification of a system, what are the different things that you look at?
Yeah, so I think that a lot of this can depend on who you talk to. It's a fractured community. You've got some of the very sort of mathsy formal proof type people, then you've got more engineering types like me that use it as a tool. But from my perspective, I look at it as in four main parts to formal methods. You have the modeling part, where you actually just forget that it's formal, but the act of modeling, creating simple models of a system or creating simulations, is hugely valuable. And so the modeling aspect alone is very important. Then you've actually got the verification part. This is where, like, the machine verification, you actually get the computer to verify the correctness of your model. And that's what most people think of when they think of formal methods.
Yep.
You've also got the promise of it being this kind of precise documentation, like no more ambiguity of like how things work. You've got it right there encoded in a simple in a simple model of how things interact. So you get this kind of precision, and you can use it as a communication tool with other teams. I'll get on to how maybe that's probably not been realized to a great extent,
Mhm.
but it's definitely one of the promises. And then the fourth thing for me, which is not very well documented, I've written about it, and it's one of the main, it's actually a really big thing for me, is using formal methods and modeling as a systems learning tool.
Hmm.
So I can break down each of those because it's quite a lot. So just to repeat, it's like modeling, verifying, like a kind of documentation, and then as a learning tool. So if we look at modeling, this is, you don't have to use TLA plus or FISB or PLANG or any of the other more sophisticated tools to do modeling and simulation. You can use Python. You can write the Python scripts, and you can explore your kind of problem space with a simple model. So rather than just, maybe you've started with a design document and you've more or less what the main components are, the different actors in the system, how they will communicate. But it's really hard to like think of all the things, all the different interactions that could happen, the order in which they could happen. I find if I can take that initial design that I've written down in diagrams and prose and put it into a simple model of maybe a few hundred lines of Python code or some kind of code, and then I can run it, I can play with it, see what it does, see interactions, I can ask questions and get answers. For example, something that's really good with simulations is to ask questions about statistical properties, right? And I've done this with TLA Plus as well, where I'm working on a gossip algorithm. How long is it going to take to reach convergence? Different gossip algorithms have different kind of strategies. So you might have, for example, an epidemic style algorithm where information is infectious at the beginning. And so nodes will be exchanging new information a lot. And then as information ages, they stop sharing. And this avoids exploding the network, amount of networking, but also ensures that information travels. So how would changing, let's just say, I'll exchange a new piece of information 3 times, or I'll exchange it 5 times, or I'll exchange it 10 times. What impact does that have on network traffic? What impact does that have on time to convergence until all the nodes know that this other node died or it joined? You can answer all these different questions. I've used models to answer questions with Kafka, such as if I got a certain amount of throughput and a certain number of brokers, how much network and disk will different configurations use? It goes beyond formal verification, but the idea of modeling and simulation to answer questions is extremely powerful. I've used it multiple times at Confluent to answer questions, and sometimes I share that in blog posts, some of the discoveries. And you don't have to run this huge complex system or even write the whole thing to find out. You can explore these questions in a simple model. And another thing I'd like to say on that point is you don't have to be a math genius, right? My maths is pretty bad, like compared to a lot of people I deal with, especially in the formal verification community. I'm not particularly gifted with math. And so sometimes when I really need some deep combinatorics to answer a question, I can't. And so I build a simulation because I don't have the confidence that my math skills will come to the right answer, but I can build a simulation and then I can gather empirical data. So I would say that modeling and simulation as a whole is extremely useful. And I think that it's probably too overlooked, even in the distributed systems community. There are some people like Mark Brooker. If you search on Google for Mark Brooker and simulation, he's written a lot about simulation as well. So that's one aspect. So bringing that back to formal verification. So the second point I said was verifying. So what if we can have a model where we can explore all the interactions and we can answer questions that to learn about the properties that the system has, but what if we can actually add some additional things on top, such as safety and liveness properties? So we can, through TLA Plus, we can create a simple model, a high-level model of our system, and then we can express properties in terms of what is the system allowed to do, or conversely, what is it never allowed to do? Like it's not allowed to lose data, right? Or it's not allowed to deliver a message out of order. Or we can't have 2 different nodes who are supposed to think the same thing actually say different things, right? So you can often express these safety properties, usually known as invariants. You can express them as in this thing should never happen. And so you can also use liveness properties. So you can say things that should eventually happen, like good things that you want to eventually happen. So using our gossip protocol example, let's say that if a node dies or joins, then eventually the whole cluster should learn of it. And if they don't, then that's a problem. So a liveness property will be eventually any change in membership will be, all nodes will converge on that same information. And so using this combination of safety and liveness properties, we can actually get confidence that our model is correct. And it doesn't have some weird, when you've got this, what seems like an edge case scenario of different interactions, it can actually lose data. Like, who knew? Like, I've broken enough systems, existing systems, to know that there's some, hard to, you just, as a human being, you're just not equipped to see some of these interactions that happen. And sometimes I learn about properties just by seeing like weird stuff that happens in my model. I'm like, okay. I've learned loads about Pymon recently, Apache Pymon, about how the deletion vectors work. And I learned most of it because I didn't actually realize a lot of what deletion vectors do and what different checks in Pymon do with deletion vectors. I didn't understand it until I wrote the model. And then the model told me all kinds of things about deletion vectors. And so verification through specifying properties, we can then use a model checker to check the model for those properties are not violated, and when they're violated, that's a bug. It can be a bug in your specification, and then you have to check that. And if it's not a bug in your specification, then it's a bug in the protocol. But there's also some other techniques for doing verification, which is not using, say, TLA plus or FISB and a model checker. There's other things. So the Amazon S3 team wrote a paper on lightweight formal methods, which was a way of doing formal verification without using TLA plus or anything like that, but actually written in the language that they implemented S3 in, or at least this component of S3. And they had written it in Rust. And it really comes down to model-driven testing. So the idea is that you can, again, create a simple model of your system. And then what your tests can do is almost like an end-to-end test. You can execute a series of commands on the real system and also your model. Now, your model should be embarrassingly simple, like in-memory model. Like, it should be so simple that it's right. And then what you do is you compare the output from the real system with the model. And the model says X, and then the system says Y, then you've probably got a bug in your system, and then you can trace back what that sequence of commands was, what led to it diverging. And then you got things like Jepsen and Maelstrom, which again is really interesting case where it's in the Jepsen IO GitHub organization, the Maelstrom repo. Basically allows you to write kind of models of distributed systems in any language you want. And then it models the network as standard in and standard out. You basically give Maelstrom your binary that you've made. Okay, if you use Java, you'll have to use GraalVM or something. And then it will use the Jepsen checkers. So you could say, I want to test this for linearizability. And it would test your model for linearizability. And if it finds it's violated, it will then print you out all the trace of what happened and what the communication was and stuff like that. So there's lots of different levels of verification, but they're all based on models and modeling. So the next thing was the documentation. And this, I think, is probably the weakest aspect for me now that I've been using TLA Plus for a number of years in industry. The use of TLA Plus as a kind of augmentation of your documentation is somewhat limited because it's actually a bit obscure. It's hard to read. You have to learn the strange syntax, and the motivated engineer will manage. But the thing is, even motivated engineers don't necessarily have time to learn it, and it doesn't necessarily, it might just be a very small elite group that will actually be able to read it. And I think that's where maybe its weakness has been, it's not just a general purpose documentation tool that you can just use. Hey, like this is all the pros with all its ambiguity removed, and we got this nice, precise, crisp model.
Mm.
And it's great if you read TLA plus, but it's not so great if you don't. And I think that's where FISB can help because it's written in Python. And my hope is that maybe if I'm in projects where I really need like a wider audience for the specification, then I would probably choose FISB, even though it's quite immature in some ways. Right now, the tooling is immature, but it's definitely improving fast. I've been working with JP over the last few months and asking him for this and that. And he's been really great adding stuff to make my life easier. So that's the third piece, which is as a communication tool and documentation. And then the final piece for me with formal methods as a practitioner, as an engineer, is that it's an amazing systems learning tool, because when I have to learn a new system, at first, imagine the first day, you have to learn this really complicated, big distributed data system, and you're now having to contribute to it. Where do you start? And you start at the code, and there might be some poor documentation, and it can be just thousands and thousands of lines of code. And where do you start? And it can be quite painful. Now, I enjoy dissecting systems and writing about it, so I've done it now to so many complicated systems, and I've got my own process down pretty well about how I do it. And at the centerpiece is TLA plus or also FISB, because what I do is piece by piece, as I learn what the different components are, how they interact, what the various checks are, I add them to the model, and I just start building an abstract version of the model. Sometimes, depending on the project, it could be quite an old project that maybe have had lots of evolution over time. Sometimes there aren't the abstractions in the code that I would like, and so I build my own just to help me understand things. And I build that into the model, and I run the model, and I start to learn how it works. And it's I found a safety violation. I made it lose data, and I go back to the code and I study, and I find, oh no, I missed this important check. Or I even create an issue and say, look, I don't know if this is a bug. Maybe it's a bug. And they'll be like, oh no, you're missing this check. And I'm like, oh yeah, there's the check. I just it was over here in the corner. And I'm like, what is this? It's not immediate. What it does from just looking at it is just checks this thing. And I'm like, how does that help? I implement it. And then it becomes clear in the model what it does and how it's important. And then what's really interesting is you can just enable and disable some of these checks, and it really teaches you what they do. Like you implement the check, everything's fine. What happens if I disable this check now? Oh, it leads to this kind of trace of 24 steps where, there was a leader election, and then a membership change, and then there was another leadership election and another membership change. And now we've actually got split brain. This is a kind of within the Raft world, there's a kind of the famous first bug which applied to how membership changes work. And it turned out that with an even numbered cluster, it was possible that with a couple of leader changes and a couple of membership changes, that it would enter split brain, where there were two leaders that were both functional. And that was pretty terrible. And so there ended up being a very simple fix. And so that's in my TLA plus model of Raft. And I can just I actually have a constant, like I can set it to true or false and say, implement the thesis bug or not. And I can turn it off, and then boom, it's like I can run it in simulation mode, and it will find it in 15 seconds, and it will just show me an example trace of how it can end up in split brain. So, it's, as a systems learning tool, it's amazing because the model will teach me a lot that I couldn't figure out from the documentation, or I couldn't figure out from the code. And I guess my first used this technique when I was in the RabbitMQ core team. RabbitMQ is a messaging system, and it uses historically a metadata store, which assumed that it was run on some telco rack with cables joining the various servers. So it assumed the network was reliable. And then people started using it on unreliable networks. And RabbitMQ got a bit of a bad name a lot because of the problems of amnesia. Finally, the team were like, we need to develop a replacement. When I joined, a prior member had written one, but no one really knew how it worked. And it looked really complicated. So I said, oh, no, I'm going to make a TLA plus model out of it. And I did. And it turned out to be safe. I couldn't find a bug in it. But there were some aspects of it that the team had no idea. There was something called blacklisting, which again, I can't remember now what it did. But no one could figure out, like, why do we need this blacklisting? Oh, it's fine. I can turn that off. I already knew because I'd implemented it and I'd seen what happened before I'd implemented it. But I could show them and say, look, let's just turn it off, run it, boom, safety violation. This is the steps. And they're like, all right, so now you know what blacklisting was for. And I could just show it with a model. That's pretty powerful stuff. And then the second time I used this kind of reverse engineering technique was when I joined Splunk to work on Apache Bookkeeper, which is a distributed log service. And it's what powers Apache Pulsar messaging system. And, I had no clue how it worked. I'd written about it at a high level, but I was thinking, if I'm going to be an engineer working on Bookkeeper, then I'd better understand how it works before I start changing stuff. And so I reversed engineered it into a TLA plus specification, and which was quite tough. I found that quite a tough experience. I think it took me about a month to do the reverse engineering and produce a TLA plus spec because there was so much nuance in the code. But I did it finally, and to my surprise, I found a protocol bug. There was a data loss bug in the protocol that had existed, for however many years. Bookkeeper had been around by that point, and multiple years. And it was actually really simple when you look back and you think, oh man, that was a really basic bug, but it wasn't obvious. Maybe I can explain it like as an example of bugs that can happen that retrospectively seem obvious, but at the time no one had thought of it. And that is the way a Bookkeeper works is that it's disaggregated storage, and you have these kind of dumb storage nodes. And then the writer that, for example, lives in a Pulsar breaker, it will itself write each record to 3 Bookkeeper servers, right? So it does the replication itself. But then if you have another writer that says, hey, no, I'm the writer, you can't have them both being able to write at the same time. That's basically split brain. So Bookkeeper solves this through a fencing operation. Basically, the second writer comes along. The first thing it does is it fences the Bookkeeper servers, basically. And the fencing basically means that, hey, no other writer but me now can write. And so once the fencing is complete, we're guaranteed that the original writer, can carry on, but it can't actually write anything. Now, fencing was based on a quorum, a majority quorum. Hey, we'll say that fencing is done when enough nodes have been written that you can't get a right quorum when writing. So we basically fence enough so that you can't get a quorum when you're writing. Great. And what no one actually took into account was that someone could already be in the process of writing. They could be halfway through a write. It could be written on say, let's just say you need a quorum of 2 out of 3. They could already have written one record to one server. And then you come along and say, I need to fence 2 out of 3. So you fence 2. But it turns out that there could be one server left, you only fence 2. There could be one server left unfenced. And that could be the one that the writer needed to get quorum. And so it was able to carry on and sneak in a few writes before fencing became complete. And I don't know if that's clear, but basically it was this kind of, in retrospect, it's like, duh, obviously, but no one saw it. I didn't see it. I was spending a month on this thing, and it was just like, oh, wow. And it turned out the fix is just one line of code, which is great. And I found that so often. I found a bug in Kafka. It's called reassignment. It's the same as Raft reconfiguration. And it's just one line of code fix. Amazing. A lot of the time, you can get lucky with just one-liners. So reverse engineering existing systems into a model, even though you're not doing it to do formal verification, do it to learn how the system works. But the process of writing that model is just incredible. You just can't keep all the moving pieces in your head. You
Hmm.
just can't. It's just
Yeah.
too many moving pieces, too many different checks, interactions. So materialize that as a simple model. And if you're using formal verification, you now just got these superpowers to add properties and make it machine executable. So
Yeah. Yeah, I think that makes sense. And just to recap a little bit, because there were so many interesting points that you mentioned and also shared some examples. First is the model and then the verification. The third is documentation. And the fourth one is systems learning, right? And probably for most people, I think the last one, which is systems learning, is going to be really interesting and like a
mm,
fresh way to look at things. But I think it requires you to think really high level and really like abstract, like when you want to create a model of something. So let's take an example here. Let's say I'm completely new to a system like Kafka, and I'm taking an example Kafka because it's pretty popular and people know about it, so it will be easier for them to relate. So let's say I want to learn how Kafka works, right? And when I say Kafka, it's really a huge ecosystem now. But let's say
mm,
I want to learn about how these producers and consumers work and interact, and how broker nodes store data and all of that.
mm.
So this itself is a big problem space. Like there can be multiple things going wrong, and there are many actors talking to each other. Now, if I have to create a really simple model, let's say, as you mentioned, not even using TLA plus or FISB, but just let's say using Python, how should one go about thinking at a high level? And you mentioned one really good point, which clicked me, because it was something like your model has to be so simple that you're sure it works, and that's the right thing, right?
Yeah, in certain cases,
Yeah.
yeah.
Okay.
The
So
simpler the better.
the,
The
the
simpler
simpler
the
the better. Yeah.
yeah.
So you don't basically have to test your model and test it for correctness, because this is how it works, and your mental model becomes more clear that okay, this part works and here is a bug. So it
Mm.
becomes easier for you to reach closer to the bug, like the actual system. So, taking this example, how should I reverse engineer, and what are the building blocks that I should start thinking about? How simple should I keep it? How should I go about writing a model so I can actually make progress and not just getting stuck with too many complex things? So, what is your approach in that sense?
So generally speaking, when we're modeling, we can choose the abstraction level as,
Yeah,
and when you're modeling a system, you can choose to first I would find out what the different components are
yeah,
and find out the gist of what their role is.
hmm,
But you can make certain assumptions, like going to Kafka. The Kafka replication protocol is separate, but
hmm,
depends on the raft-based metadata component
hmm,
called the kraft controller.
yeah,
Okay. Now, the kraft controller is a raft state machine, and raft itself is actually quite complicated, simple conceptually, but nuanced in the details. But you know that, for example, raft gives you certain guarantees.
hmm,
And so when you're doing your modeling, you don't need to model raft. I can just model the controller
yeah,
as like a single thing. It's not distributed. In reality, it's distributed, but I don't have to model it as distributed because I know in theory, if it's implemented correctly, that it can basically almost act as if it was just a single component, a single process. And so you can do that, and you can just abstract all the complexity of what's below the interface of this controller away. And you can just assume that when you write to it and it says, okay, then it's okay. You don't have to worry about all the complexity that goes below it. And you can choose to do that with many different parts of the system. You can just abstract those parts to the level that you want and maybe just focus on one piece. Or maybe you
hmm,
want to abstract everything and just start with a really simple model of like, I've got one controller, I've got three brokers. Let's forget that each broker could have hundreds or thousands of partitions. Let's just say one broker, one partition. We model a single partition. And then you've got, you know, the simple logic of every you could do there's various techniques. You could literally just in a loop figure out who needs to do what and say, oh,
hmm,
this guy needs to send a request this broker should send a request to this other broker, and then that broker will respond using a very simple in memory. You don't have to actually write any message passing.
Yeah.
You could have them as different objects in memory.
Mm-hmm.
Maybe you could abstract the network in some way with the queue, or you don't even do that. You just do these kind of atomic communications. Hey, I communicated, I sent the message. And it's like I basically just reached into the other partition and said, here, have this. And so you can really like make things simple, and then you can just run it, and you can, again, with these models, you can then use model-driven testing to have really simple, like you've modeled, say, Kafka in Python, very simple, highly abstract version, but then you might even have your kind of correctness model alongside, which is literally a queue, like the queue type that
Yeah.
every language comes with a queue. And you just can verify, you can just verify the output of your simple model with that actual queue type and give you confidence that your model's right. So I would say that the fact that you can choose your abstraction is what's so powerful, but it also, I guess, can make it hard when you're not used to modeling, because what abstraction should I choose?
Yeah.
And I can only really say that the way I start writing a specification is to learn what the different actors are, about their communication lines between them. And then each kind of communication, what does it consist of? What data? And what kind of essential state in each of these actors is mutated based on this message passing? Okay, I need to add that. And I slowly like start adding fields. Imagine like each actor is like a class, and you've got these kind of private fields. And then you've got these kind of other classes that are almost like a message. And you just slowly figure out what the communication lines, what is their local state that they manage based on these message passing. And then there's things like if there's triggers, right, for when certain things happen. So what are the triggers? Like what will trigger the control plane to kick in to sort things out when things go wrong? Like a broker has failed, or the controller will now kick in and do stuff. Well, what are those things? Okay, so all right, how does the controller talk to the brokers? What is contained in those messages, and what impact does that have on the broker? And does it then communicate with another thing? And you're just tracing the highest level you can, the communication lines and the repercussions of when this will trigger a broker to contact someone else, and things like that. And also you should be thinking about, what is this system? It's Kafka. So what are some of the guarantees that are like famously written about? It's replicated for fault tolerance, ordering at the partition level. So you can figure out some safety properties that say if the producer sent message A then B, then a consumer should also read A then B and not the other way around. To start thinking about the properties that the system has and just go from there, really, and just evolve it as you go.
Yeah. Okay. I think that makes sense. And so I think the idea is to follow like an incremental approach and decide on
Yeah.
your abstraction level and what exactly that is, that what you want to test or what you want to learn, and then really think about like the data structures that are involved and the actors that are involved. Like when you say, okay, I produce a message, what could it mean in its simplest form? When it says broker has a partition, what would it mean in its really simple form? I think the idea is to not complicate it and really keeping it simple, and then incrementally adding complexity to it, right? Because
Right.
if I have to do it, I would really go simple and do it, but then how do you keep extending the complexity without needing to change your model a lot, keeping it extensible so you don't have to like really change the model a lot? And I think it will help if the core abstraction is correct, right? If I take a topic as a queue, I think that semantics is not going to change, right? Even if we add more and more features. So are there
Yeah.
any more tips and tricks that you would like to share? Like how do you make sure that, for example, where this is coming from, right? So I was trying to create a parallel line with it. When I say, let's say I have to test a code, I write some tests, right? Like I write some tests and then
Hmm.
I also create some mocks, and it's the same kind of exercise that I'm doing, right? I create some mocks, I just produce some inputs. I say, okay, for this input, just fail and see what's the behavior. So I'm doing kind of the same thing. So my test is
Mm.
actually the model of what is going to test. Instead, in my test, I'm actually calling the code and verifying that it works, right?
Yeah.
The typical problem I've seen with that is whenever my code changes, I have to also make changes to my test. And then
Mm.
sometimes it can be like a huge change and the way it works. So does it also apply to like creating a model, and how do you keep
Yeah, I
track of
think there's
those
some
things?
parallels to kind of software engineering practices of decoupling, encapsulation,
Yeah.
modularity, information hiding. The more
Mm.
tests that you write on like the private internals of a component, the more likely you're going to have to change a lot of tests when you
Yeah.
change stuff. You might not change the kind of interface, the
Mm.
API of that component, but you might make some optimizations and changes. And the more tests you have that cover these kind of private details, the more chance you've got of breakages. So I think that making modular decomposed specifications is good. It's
Hmm.
not particularly easy to do that in TLA
Yeah.
plus. Probably something that I miss is actually hard for me to make to do really good decomposition and modularity while also not making other things more difficult.
Mm.
But one of the also things that you want to do in distributed systems is encourage as much decoupling between components as you can. And so I would say that if you've had to change one component and its internals, and that's now had mean you've had to change some code somewhere else, that might actually
Mm.
be an indication that your design is not optimum. You want each component to be as independent as possible and just, its
Yeah.
public API, whether it's the messages, its exchanges, or whatever. Now, where it can affect a say a TLA plus or FISB specification is in your invariants, because your invariants are naturally reaching in to the private state of each component.
Yeah.
One thing that is really powerful about TLA plus and FISB is that you have access, your invariants, which are essentially like your tests, have access to the global state of the entire system.
Mm.
And they have an atomic view, because the way TLA plus works is that it takes you from one discrete step to another. Time is discrete. You go
Yeah.
from, hey, the system as it is now, where we have, say, counter one is at 2 and counter 3 is at 4, to another state where the counters have different values. And you
Mm.
go from like each step takes you from one state, like a global state, to another global state, to another global state. And then your invariants, which are like, I guess, your tests, can basically inspect the values of all these variables. Um, and so when you change the variables, you have to change your invariants. And sometimes if you have to change something, it's, oh no, now my invariant doesn't work or has to be modified. But I would say
Yeah.
in general that one thing that happens is that change doesn't happen very often. Like the kind of the protocol for how Kafka brokers talk to each other does not
Mm.
actually change that much. If you look at all the commits, there's daily commits, thousands and thousands of commits. But there's actually a much slower cadence of changes that affect protocols. And so what
Mm.
you'll find is he'll be like, in fact, I'm been asked right now to come back to the KRaft spec and check it against the latest changes. But the last time I worked on that specification was probably about 6 months ago. So things don't change that often. And you've got a small model,
Yeah.
and so it tends to not be too much work to make changes. That said, it depends on the complexity of the model. My Kafka replication protocol model is grossly complex, I'm afraid. I just wanted it to be faithful down to it's faithful at a logical level. Like I'm not getting into programming details, threading models or disks or anything like that. It really is just down to the protocol, but it's enough little bits that if I wanted to be uh, faithful to the protocol, I had to make it quite large. And so there is a cost now. If I want to, for example, I have to review this pre-vote change. It could take me a couple of days to make the change, get confidence. Actually, it can take longer
Mm.
because you run it because we're doing model checking, right? So model
Yeah.
checking can take days, right?
Mm.
Because you have this kind of exponential increase in state space as you add more messages and you want to test now 5 servers instead of 3. There's massive exponential increase in the state space. I don't know if we want to actually talk a little bit about what the state space is and stuff, but generally the bigger it is, the longer it takes to check. And so the whole process might be like a day to make the change,
Mm.
maybe another day on and off, finding little problems I've made, little bugs I did, and
Mm.
then I got to leave it for a week and just let it run
Yeah.
and hope it comes out with nothing. Um, but yeah, change is not often, at least in distributed systems, change doesn't happen that often. It just happens
That
in
that's a
spurts.
that's a fair point. Yeah. And then when I think about these, so there are these existing systems that, they have protocols, they have specs, and they have been running since many years. And then there are new systems that people are building, right? For example, when Kafka moved away from Zookeeper and they were
Mm,
working on Kraft. So how does the approach change when it comes to, let's say, testing or writing formal verification for an existing system
mm.
versus something like a new system like Kraft? How does that change? I would imagine that the model building and that kind of thing is going to stay the same. But what
Mm.
I'm getting at is there are more changes coming in when you're building something new versus when it's a stable system, right?
Yeah, so the way it's worked for me is there's been a couple of cases where I've designed a protocol. It could just be experimental as a demonstrator of, hey, we could invest in this. This is a replacement for something else that doesn't work.
Yeah.
And I go through the process of what are the properties I want, what do I want it to do, what are the components, and I go through maybe an initial pass, create a
Mm.
model, and then I start sharing it with others. Now at Confluent, the kind of formal verification team is mostly me. There's Jason Gustafsson. He left, so he was the kind of guy before me. So I work with teams. So the way it's working at Confluent is either I'm proposing or other people are proposing. We either co-design it or maybe even I'll come in just after the fact and then I'll model it and then
Mm.
goes into the process of actually the engineering team implementing it. They will then, it turns out that, oh, my idea wasn't very good because actually, I didn't know Kafka very well at the time when I proposed it. And there's like, this component shouldn't talk to that component. And because of XYZ. And oh, yeah, you're right. That really shouldn't. And then they propose changes. They implement the changes. We find problems. We go back, we look at solutions. I like, okay, let me check that solution in the model, implement it in the model. A couple of days later, I come back and say, well, that works. And then the engineer has said, actually, I don't like that. I want to try this other thing. And so again, we go back to the model, test it out. Yeah, this looks good as well. So really now you've got 2 options that can work and you have to choose which one suits other properties like
Yeah.
performance. Like one thing that, models can't always do, performance. Some things they can do, they can say, this is way too chatty, this protocol. It's
Mm.
like too many messages have to be
Yeah.
exchanged. But other things, it doesn't have, it can't tell you about the performance. So
Yeah.
then you have to come down to the age old engineering, software engineering discipline to figure stuff out. And again, more changes might be needed, but not because of there's a better protocol, but because of some other realities within software engineering that
Mm.
make the original choice maybe subpar. So that's this process that I've used. I used it at RabbitMQ as well because again I was not an Erlang programmer. So when we were designing the new metadata store, no, not the metadata store, that came after I left. The RabbitMQ streams. It's like
Mm.
a Kafka type. It's like a distributed log rather than
Mm.
queues. Again, it was like let's figure out how it should work. I built a spec and then we iterated it, and then Carl, the main engineer, started implementing it, and then it's back and forth between the formal verification engineer, which is me, and then the engineer. Now if you can actually have the engineer writing the code be also the formal verification engineer, then that's great. That's what I was doing at Bookkeeper, Again, we did modifications to the protocol so that it could run without the journal, like run without a write-ahead log. And then we had to introduce changes into the protocol so the protocol would be able to recover in scenarios where a bookkeeper server said, yes, I've got your data, and then later it loses it because it's not writing it to the write-ahead log anymore. And then the protocol needs to have a recovery process where it's able to repair the loss of redundancy. And so it really depends on who you've got who can do the formal verification. In my case, I'm not a Kafka committer, but I work with Kafka committers. I understand how Kafka works fundamentally. I'm not writing Scala code, so I just work hand in hand, and it's just a process of going back and forwards and modifying things.
That makes sense. And so let's say you have an existing system and the product team is working on it, and you are running some formal verification and you find a bug, and then you go back to them and say that, oh, you know what, in this case this may not work, or this guarantee may fail. What are the next steps? I want to understand that how this. So let's say, so you're sure that, okay, your model
Mm,
works, and then you're claiming that this is where the problem may exist, and then there is the real system. Like, how
mm.
do you make sure that you reproduce that and actually prove that, okay, this fails on the the actual system, and then prioritize the bug fix or something?
Right. Sometimes it can come down to just writing a test. Most of these distributed systems give you hooks so
Yeah.
that you can control things under the hood. You can set up scenarios in a test, and you can literally hard code a sequence of actions
Yeah.
and show, look, it just lost the
Okay.
data. And actually, that can be very effective, at least for
Yeah.
confirming it that it exists.
Hmm.
You know, but this is when you know, like, it's over there. So you go there and you write the thing, and that's very commonly what I've done is just write a test and then show the failing test. There's nothing like a failing test to back up the claim. Other times you don't even need a test. Like the engineer will be like, wow, Jack, wow, like it's clear now, like that will happen. Like no doubt. And that's happened. And in other cases, I've left feedback for other teams and I haven't always had a response and just left it at that. So I don't know. I've got one open right now for Iceberg and I've had some initial response, but I think they want me to write tests, but I'd have to learn how to write Spark. There's basically, I don't understand the hooks for how I can add the hooks I need to Spark so I can so I can set up this sequence of actions,
Yeah.
which pretty damn sure is possible for
Hmm.
Spark Iceberg to lose data. I don't know how likely it is, but I know, TLA Plus shows me it's possible. Yeah, so tests. And then, generally after that, if you've got your randomized testing, like your Jepsen tests, or if you've gone the next level up and you've gone for deterministic simulation testing, which is, it's like randomized tests, but you get a seed so that you basically eliminate all forms of non-determinism that you
Yeah.
can by, for example, using a random number generator based on a specific seed. And then the idea is that you can run all these randomized tests and do all these perturbations. A lot of this can be, stubbed out. It can just all be in memory, like on a single server. And then you can like hammer this system with perturbations and, you find, a property gets violated and then you can identify the seed and then you can then recreate it, because one of the big problems with Jepsen is like it'll give you this huge numbers of thousands of lines of logs and hey, this is the trace, and it's, oh my god, I can't even read that. And then you're studying the logs and you're trying to work out, and it's just a nightmare. So if you can just have that seed, and then you can even maybe you can even debug, you put a debugger in if you've managed to do it all in memory in a single process. Obviously, it won't tell you necessarily that you fixed the bug, because by fixing the bug, maybe you change the behavior, which means that seed is irrelevant now. But then you can just run the whole thing again and
Again, yeah.
hopefully give you confidence. But that's really it can take. The trouble is that TLA Plus doesn't actually. There's no difference between events that happen very often and events that don't happen very often. So, for example, okay, we're talking about the Kafka replication protocol. In steady state, you could be sending 1,000 records a second. And then once every week, there could be a leader election, right? But with TLA plus, it'll be like leader election, replication, leader election, replication. It doesn't care.
Yeah.
It will just, explore the entire possible state space. And so it's able to find these really hard to find interactions and able to find it really quick. For example, going back to this raft problem where it required an even number of nodes, it requires 2 reconfigurations and 2 leader elections where the second leader election elects the original leader. Okay. My TLA plus spec just like, boom, got it. Whereas I bet you if you run that in Jepsen, you could run it for hours and hours, days. Maybe you might not find it. Maybe I don't know the history of how they found that bug. It could have just been through thought process or something.
Yeah.
But that sometimes can also be a problem because sometimes you're like, wow, this is so obscure. Like this would never happen. I found a really obscure one in Kafka to do with the way that when partitions can move back and forth, if they move back and forth 3 times and there's a leader election at just the right time, this particular thing could happen. And it was just like, what are the chances? I bet no one's ever seen that in the history of the world.
Yeah.
Because it's so obscure. So sometimes you have to balance as well. It's like, it's good to fix these things, even if it is maybe very theoretical. Yes, it's possible. But also, if you're running things at scale, 1 in a million things happen every day, at a certain scale. There's arguments to that. But
Agreed. As they say with distributed systems, it's not the question that if it will happen, but it's more about when it will happen. And that finding that when is the tricky part. It may never happen if you're lucky. It may happen just the next day if you're unlucky. And I think it's about discovering the unknowns and at least having them documented so we know the risks. And then based on the risk, probably prioritize the fix as well. And okay, before we wrap this discussion, I want to ask you last question, which is about, since you have been working very closely with these tools and the verification system itself, how do you see this will change in the coming future? Or I want to ask how it will become better in terms of toolings, in terms of adoption, and what are your thoughts on that?
So I think that we're already seeing like different tools emerge. So TLA Plus is so powerful, and now I've been using it for so many years. It's like it's my superpower. It gives me an edge. It helps me, do so many things. But at the same time, trying to find engineers who are willing to write it is very hard. It's hard to read. Some of the aspects of it around liveness can be really nuanced, but powerful. So then you've got other things like FISB. Now, FISB, one thing that's nice about FISB is that it solves, I think, greatly the readability problem, but still gives you essentially the same semantics for how safety and liveness works. You have a global state space, so your invariants can look at the entire world and say, oh my God, the message exists nowhere, because you can see it everywhere. But then you've got other systems like PLang, which is a bit more opinionated. And I think it's easier for engineers to get started because it's literally, you're basically running state machines that can communicate over an ordered network. Like it has opinions, like the network is ordered. You don't have out of order messages, right?
Okay.
And for some people, they'll be a lot more productive. So I think it comes down to making it simpler to write these specs. And I think FISB is one, which is very much a TLA plus oriented, which is why I like it. Then you've got PLang, and there's probably others that will come in the future. But I think it's really got to be about simplicity. I think that it will forever be somewhat niche, at least as it is in its current form, because you don't need formal verification for a CRUD application. Or most where it's like amazing is concurrent systems, distributed systems, which are concurrent. But I can imagine in the future that we could use this technology to more on like business processes. Could hackers like buy and then like make orders and then cancel orders and then change orders and then make a phone call and then suddenly they got all this free stuff because they hacked your business process, right? And a business process is a concurrent distributed system. It's just one made of humans and processes rather than like code, like one code system.
Yeah.
I remember watching a YouTube by Jay Parler talking about Alloy, which is
Mm.
another tool, verification tool, talking about how he used it to verify a data model. And so there are some other use cases. I would look to business processes and security in general as another avenue, but I doubt we'll see this kind of design verification
Mm.
getting beyond too much more beyond distributed systems, maybe business processes.
Yeah.
What could be true maybe in the future is some code-based verification. It's been worked on for 50 years so far, and we're still not gone mainstream yet. So
Yeah.
I wouldn't hold my breath.
Interesting. Jack, thanks a lot for sharing all the experiences, all the insights, and I'm particularly interested in the fourth section that you mentioned about systems learning, because that's probably the,
Yeah.
the closest I'll get to formal verification based on the experiences I've had so far. And yeah, thanks a lot. And I, for our viewers, if you want to know more, look at Jack's blog, and I'll also make sure I add the link in the YouTube description, so you can find Jack on Twitter and LinkedIn and probably connect. So yeah, thanks a lot. I really
My
enjoyed.
pleasure. I'm always happy to talk about formal verification. It's a passion of mine.
Awesome. Thank you.